have also really with raw eggs fixed.
Right. So we're starting out with motion in a straight line. This is on page 4. And with our motion in a straight line, we can superimpose this without thinking of the number line, which you probably did in like grade 8 or something, the number line. We follow along with our usual convention of calling this the x-axis, if you like. So I'm labeling it. I know it's not straight, but it's straight enough. Okay, again I'm using some physics conventions here where I've put the label of the axis on the positive side. This is telling me that this is positive x. What does that mean? Well, if we're talking about moving so that our motion is in a straight line, what that means is if I move in this direction, I'll write. So if I move in that direction, it's positive. Now it doesn't matter where I start. So I could start down here and move in that direction and it's still positive motion because it's in that direction. Now, motion, actually I decided that the orange one didn't look too much right. So I'll go with red. Hopefully this isn't a big leap. So motion in this direction is negative. Does that sound fair enough? Oftentimes the direction is sort of given in the question, but if it's not, you can set up your coordinates so that you can explain your calculations. And our convention is always that positive is to the right and negative is to the left. Okay? We'll have a bit of a read here. The motion of objects can be described by words. This is one of the problems, is that in science we have specific meanings for words, but some of these words are also used in general conversation or general dialogue, and they can have a broader meaning in conversation, but often they have very specific meanings in science. So we're going to need to make sure that we're using our terminology correctly. So, going fast, stop, slowing down, speeding up, turning, they're all talking about the motion of objects. But we are going to speak specifically about distance, displacement, speed, velocity, and acceleration. And as I said, they have strict definitions. Now, if we look at the example on page 4, we've got Sophie, and she's a swimmer. And she's doing laps in a 50-metre pool. And her position is her location with respect to the origin. So, on my number line, this is the origin. And for those of you doing maths, I'm sure you've talked about 0, or the coordinate 0, 0 on the Cartesian plane as being the origin. So it's the same thing here. That we're saying that's the starting point, if you like. And so for her, in that example, we've got a swimming pool, and she's standing here. the end of the pool is the origin in this example. It's 50 metres long, it's an Olympic pool, and she's warming up here 10 metres from the end of the pool. And so, because we know that our number line here is saying that that direction is negative, the pool has been set up this way, tells us that's another clue that direction to the right is positive. Then this must be minus 10 at this position. Is that everyone okay with what we're doing so far? Okay, so while she's warming up, she's at minus 10. And then when she moves to the end of the pool, at the starting block here, she's at the origin, 0. So she's moved 10 metres in the positive direction. Now, when she has swum half of the length of the pool, then her location is at plus 25 metres. Is that okay? Because we're only explaining her position in terms of x. So she's plus 25 metres from the origin when she's here. If she swims the full length of the pool, then she's here. Okay? And so this would be plus 50. What happens if she swims back here to this point here? Where is she?
25.
She is still plus 25. That's right. So that is her location, would be plus 25. How far has she swum?
75.
She's swum 75 metres, but she's only 25 metres from the origin. And so there's two things that we need to consider. There's distance and displacement. Now the distance, this is the actual distance covered, traversed. Okay, so that's, if she swam, put this on here in a different colour. So if she swims this, and in fact, if we say that she started out by warming up, then her distance would be 10 plus 50 plus 25 is 85 metres at this moment in time. Is that fair enough? Okay. Whereas the displacement is her position with respect to the origin. And in that way, it's like having a string attached to her, or an elastic band. Okay, how far away is she from the origin?
25 metres.
She's 25 metres, that's right. And so when she was here, we could imagine, the elastic bands stretched back that way, and then she stood here, and the elastic band just hung off her. And then she swam all this way up here, and it stretched 50 metres. But then as she came back, it wasn't stretched anymore. And so displacement is like the elastic band. It's just measuring how far you are from the origin, or your position with respect to the origin. Sorry, it's not measuring how far you are, it's your position with respect to the origin. And so in that instance there, yes, her position is 25 metres. Because our measurement has to come from here. This all sounding like the stuff you've done before? Okay. Now, because this one doesn't really matter which way you go, which way you travel, this one is called a scalar quantity. Which means that it has magnitude but no direction. Okay, magnitude. Whereas our displacement is a vector quantity. And it has magnitude and direction. And the reason why we have direction is because, remember, we're measuring it with respect to the origin. So we need to know where the origin is and where the person is to be able to say what the displacement is. Has everybody heard of scalar and vector before? Okay. And so hopefully you realise that even though at the moment I haven't written in a direction, I sort of have, in that this is a positive number. And because I've defined, because this is one-dimensional motion along just the x-axis, I am expressing the direction with just whether it says it's a positive or a negative number. So if we thought about, well, what about when she was behind the blocks back here, just so she's in this position here, then her displacement there is minus 10 meters. And it's the negative sign there that's giving you the direction. Okay? So, quite sure if you're all just tired after lunch. Where do I put it? Alrighty. And so on page 5 there are some calculations for some different examples of her swimming in the pool, where we've been talking about displacement here. For distance, we just add up how far she travelled. We've talked a little bit about scalar and vector, in that scalar has a magnitude but no direction. So, for example, here we have to have the meters out for our units to indicate the magnitude, but we're not worried about direction, whereas for our vector quantities, they have to have magnitude and direction. And for one-dimensional motion, we just indicate it with the sign. And our convention is, because we're lazy, we don't write the positive sign for positive direction, but we must include the negative sign for a negative direction. Now, how about you have a little read through, and then, so from pages 4 to 6, there's a worked example on page 6, and if you want me to, I'll go through that with you.